Hello, good morning. Acid and base, Lewis concept. Base, it is a substance which can donate pair of electron or electron pair donor is called base, and acid is substance which can accept a pair of electron or electron pair acceptor is called acid. In case of ammonia, donates the electron pair, so it is the base. The fluoride ion also Lewis base, and this boron trifluoride is the Lewis acid electron pair acceptor, and this is the electron pair donor. In the following reaction, each of the two ammonia molecules Lewis base donates a pair of electrons to silver ion, the Lewis acid. Lewis base, Lewis acid, silver is Lewis acid, and as acid base adapt. Hard and soft acid base Pearson's concept. Hard acids are those acids which the acceptor atom are small in size, high positive charge, and possess no valence electrons, thus hydrogen ion, lithium ion, sodium ion, magnesium ion, aluminum ion, chromium ion are the acids. Soft acids are those acids which the acceptor atoms are larger size and low positive charge and also contain lone pair of electrons in the valence shell. Example, copper, silver ion, aurium ion, bromine ion. These are the soft acids. Hard base are those bases in which the donor atom has high electronegativity: nitrogen, fluorine, oxygen, ammonia, amine, water, hydroxide, fluoride. Soft base are those bases in which the donor atom has low electronegativity: iodide, cyanide, iodide, bromide, etc. Hard soft acid base is a principle. It states that soft acid prefer to bonding with soft base and hard acids prefer to bonding with hard base. This means that hard acid and base are from stable complex. Similarly, soft acid and base also from more stable complex. Bonding between hard and soft species are not stable. Therefore, this principle is very useful predicting the relative stability of complex. Example, silver iodide is more stable than silver fluoride. In silver iodide, silver ion is soft acid and iodide is soft base, and combination between soft acid and soft base are more stable. On the other hand, fluoride is strong base and combination between soft acid and strong base is not stable. Silver iron is soft acid, iodide is soft base, so silver iodide more stable. Silver soft acid, fluoride hard base, silver fluoride is less stable. Cobalt hexafluoride is more stable than cobalt hexaiodide because cobalt third is the hard acid and fluoride is hard base, more stable. But in case of iodide is the soft base, so less stable. Why cobalt hexacyanoiodide and cobalt triamino fluoride are stable, while cobalt hexacyanoiodide and cobalt pentaamino iodide are unstable. According to the Jorgensen's, in a complex compounds, combination of hard lesions of soft lesions with metals ion is more favorable than combination of hard and soft lesions. In cobalt hexacyanoiodide, the metal is combined with the soft base cyanide in iodide. In cobalt triaminofluoride, the metal is combined with the hard base ammonia and fluoride, hence both complexes are more stable. But later to complex, the metal is bonded with a mixture of soft and hard base, therefore they are unstable. Conjugate acid-base pair, when acid loses the proton, the residual part of it will have tendency to accept the proton again. Thus, it will behave a base Such pairs which differ one another by the proton are known as conjugate acid-base pair, hydrochloric acid and water, hydronium ion, chloride ion, hydrochloric acid, water is base, and hydronium ion conjugate acid, and chloride is conjugate base. Conjugate acid-base pair, weak acid, weak base, strong acid, strong base. Weak acid is the acetate ion conjugate acid, and this is the weak base conjugate acid base pair. This is the weak acid and weak base strong acid, weak acid and base. These are the conjugate acid base pair. Hence, hydrochloric acid and acid because it donates the electron to water, forming chloride, which is its conjugate base. Similarly, the water is a conjugate base which accepts a proton to form hydronium, which is its conjugate acid. Similarly, water and ammonia also produce the conjugate acid base pair. Water and ammonia conjugate acid base pair. These are some as the conjugate acid base pair. Every strong acid have weak conjugate base and weak acid have the strong conjugate base explained. It is considered, for example, hydrochloric acid in water produces hydronium chloride ion. Hydrochloric acid is a strong acid and it has the strong tendency to lose H plus ion in chloride ion. Hence, the equation lies very much to the right. This indicates that chloride ion has very less tendency to gain the proton and hence BF is the weak base. A strong acid H plus with base similarly in the following reaction acetic acid water hydrogen ion and acetate ion. Acetic acid is a weak acid and it has strong tendency to accept the proton and it behaves strong base. Weak acid is plus strong base. Factors affecting the relative strength of acid and base: effect of solvent, the substance which exhibit their acidic or basic property in solution. The solvent plays very important role in the acidic or basic strength of the source substances. Effect of solvent on the strength of acid in water, that is the leveling effect. The tendency of water to equalize the strength of many acid or base is termed as the leveling effect, and hence what is called leveling solvent. In aqueous solution, the extent of dissociation of acid depends upon the tendency of the water molecules to accept H plus ion, that is on the basic strength of water. Water acts as good base towards all common strong acid like hydrochloric acid, sulfuric acid. They are almost completely dissociated in aqueous solution such that all of them appear equally strong in aqueous solution. The strength of acid in acetic acid is differentiating effect. The solvent in which stronger acid ionized to different extents so that the relative strength of acid can be measured are known as differentiating solvents. For example, acetic acid is a differentiating solvent and acetic acid is weak acid and it also behaves as a base to some extent, that is accept proton. Nitric acid and acetic acid nitrate base okay. Therefore, even strong acid feebly ionized in this solvent, that is strong acid acts as weak acid and acetic acid. Effect of solvent on the strength of base in aqueous solution. The relative strength of base depends on the tendency of water to donate hydrogen ion, that is on the acidic strength of the solvent water. Water acts as the weak acid, that is acts as the differentiating solvent for base. On the other hand, aniline acts as the weak base, and water appears to be the strong base when dissolved in acetic acid as solvent. Effects of substitution on the relative strength of acid and base. The relative strength of acid and base is greatly influenced by the nature of substitution, that is electron releasing and electron withdrawing groups and their number present on them. Effect of electron releasing groups on the strength of acid. Electron releasing groups increases the electron density between hydrogen donor atom and hydrogen, which decreases the polarity of the bond. This hinders the dissociation of hydrogen, and acidic strength decreases. Example, acetic acid is stronger than propionic acid and propionic acid is stronger than methyl propionic acid. Number of electron releasing groups increases. Electron density between hydrox-OH group bond increases. Strength of the OH increases. Polarity of OH decreases. Rate of dissociation of hydrogen SS plus ion decreases. Acidic strength decreases. Effect of electron releasing group on acidic strength. Let us consider the comparison of acidic strength of acetic acid, fluoroacetic acid, and difluoroacetic acid. Number of electron withdrawing groups increases. Electron density between the OH bond decreases. Strength of OH bond decreases. Polarity of OH bond increases. Tendency of hydrogen dissociate S plus increases. Acidic strength increases. Effect of electron releasing group on the strength of Lewis acid. Let us examine the strength of flowing Lewis acid. Basic strength ammonia, methenamine, dimethylamine. Number of electron releasing group increases. Electron density of nitrogen atom increases to tendency to net electron pair increases. Basic strength increases. Effect of electron withdrawing groups on the strength of Lewis base. Let us examine the strength of flowing ammonia, ammonium fluoride, difluoride, and trifluoride. Number of electron withdrawing, that is the fluorine groups, increases. Electron density of nitrogen atom decreases. Tendency to donate to lone pair decreases. Basic strength of Lewis base decreases. Steric effect: triamine amine, methylamine, and ammonia. Okay, sorry, dimethylamine, methylamine, ammonia, and trimethylamine. Trimethylamine should be strongest base, but it's the weakest in the above series due to the steric effects. This electron withdrawing capacity of nitrogen is hindered due to presence of three methyl groups, ball groups, and hence basic strength of trimethylamine is very poor. Effects of electronegativity. Strength of acid increases if the electronegativity of central atom increases. Let us examine the relative acidic strength of the molecules methane, ammonia, water, and hydrogen fluoride on the basis of electronegativity. Electronegativity of atoms carbon, nitrogen, oxygen, fluorine increases. Ability to withdraw electron pair increases. Polarity of X hydrogen bond decreases. Tendency to dissociate S plus ion increases. Acidic strength increases. In the above molecules, hydrogen is covalently bonded to carbon, nitrogen, oxygen, fluorine, whose electronegativity increases in the order carbon, nitrogen, oxygen, fluorine. As the electronegativity of central atom increases, the halogen-hydrogen bond becomes more polar, more ionic, and hence tendency to dissociate hydrogen as S plus increases from methane to hydrogen fluoride, so that acidic strength methane, ammonia, water, and hydrogen fluoride. However, this rule is not valid for the halogen acids, so Relative acidic strength cannot explain on the basis of electronegativity because it gives the opposite order. Atomic size of halogen atoms increases, strength of halogen and hydrogen bond decreases, rate of dissociation of hydrogen H plus ion increases so that acidic strength increases. So oxidation state, the relative strength of acids of the element is determined by their oxidation state. Number of oxygen atoms bonded to chlorine increases, electron withdrawing effects increases, electron density between oxygen and hydrogen bond decreases, polarity of oxygen hydrogen bond increases, tendency of the hydrogen to dissociate as H plus ion increases, acidic strength increases. So acidic strength. However, a series of oxyacids containing the different halogen atoms but same number of oxygen atoms, that is the same oxidation state, the relative acidic strength is determined by the electronegativity, that is the acidic strength decreases if the electronegativity of the halogen atom decreases. Electronegativity of halogen atom decreases, electron withdrawing effect decreases, electron density between the oxygen and hydrogen bond increases, strength of bond is increases. Okay. Thanks for watching and request you all like, comment, share, and subscribe. Thank you for patience. That's now bye bye. See you again.